Hello everyone. Today's video is on 2 degree of freedom free and forced vibration system worked example. In last video, which was on 2 degree of freedom free and forced vibration, from that video we learned how to find natural frequencies of 2 degree of freedom system, how to draw mode shapes of the system, and how to find force vibration response in time domain. So this is a 2 degree of freedom vibration system where two springs K1 and K2 are connected in parallel. M1 can move independently and M2 can move independently, and that's why we say this is 2 degree of freedom. M1 and M2 has connection to a spring K3. A force is applied to mass 2 and K4 is connected to the ground, and it says the position in the figure is in an equilibrium position where Ft equals 0, which is the force, and for this system the values are given for calculation. Alright, so for this system we need to draw free body diagrams for two masses. We need to write equation of motion in matrix form expressing the content of each matrix or vector. We need to draw the mode shapes of the system, and qualitatively we need to draw the frequency response functions of y1 and y2 to the input Ft, which is equal to F0 cos omega t. So as we discussed earlier video that we need to follow these steps. So starting with the first step, which is a free body diagram. So let's consider that this is unit vector. So these are the positive convention for two unit vectors, and we want to start with the equivalent spring stiffness for spring 1 and 2 because they are in parallel, so we get their summation which is K1 to equal K1 plus K2. And then let's consider first mass. Now let's consider all the forces acting on it. So because it is connected to ground in both sides, so we get two reaction force, R1x left side, R1x right side. This is negative because this is the opposite direction of this positive vector. Now this mass is connected to spring 1, 2. Now this mass M1 is connected to equivalent spring stiffness, which is K1, 2. So the force acting upward is K1, 2 del L1, 2, and downward forces are weight of mass or gravitational force of the mass, which is negative M1g, and spring force for K3, which is negative K3 del L3. Similarly, we get all forces for mass 2. So because M2 is connected to spring 3, so we get spring force K3 del L3, and also forces acting on it, so we get F, which is upward as shown in figure. Downward forces are gravitational of the mass and spring 4 force, which is negative K4 del L4. And again, similar way on left hand side and right hand side we have force. One body diagram which is our first answer of these questions. Next is to write Newton's law equations. So again we start with mass 1, and if we just look at the free body diagram of this mass, we can see that because the mass is moving only vertical direction, So in horizontal direction there is no displacement as well as no acceleration. So if we write this equation, fx summation of fx equals to m1 acceleration in x direction, this acceleration will be 0. So substituting this value, we get right hand side reaction to the left hand side reaction. In case of summation of vertical forces, we have summation of Fy equal m11 a1y. Now this acceleration, we consider that the vertical displacement of mass 1 is y1, so the acceleration of this displacement is the second derivative of y1, and we can say that this is equal to acceleration 1y. So we write all the equations acting in vertical direction. So because this is acting positive direction, so we write k12 del 1 2, and these two are acting downward, which are negative, so we write negative m1j negative k3 del l3, and that's our equation 1. For mass 2, I'll not explain horizontal component because this is the same case for mass as mass 1. Let's consider vertical forces. This time we consider mass 2's displacement as y2, so the acceleration of mass 2 would be second derivative of y2, and that's what we get as a2y. And the forces acting on mass, which is upward, they are positive, so k3 del l3, so we get k3 del l3 plus ft, which is a force, external force, and we get two negative component acting downwards, so which is negative m2g and negative k4 del l4 equal m2y2. Let's consider this is equation 2. Next step is to express all kinematic quantities as a function of selected coordinate. So in this case we'll express all the kinematic quantities as a function of y and y1 and y2. So now we want to consider three cases. So this is the first case, which is the static equilibrium. So at static equilibrium we get three static deflection of the three springs. So we write these expressions for each spring. Del L12 has del L12 static, del L3 has del L3 static, and del L4 has del L4 static. Our next case is we consider M2 stays at his position while M1 is moving upward at a displacement y1. So let's see what it has effect on the springs. So the first spring, which is k12, it will be shortened or compressed. So the expression for this one will have negative y1, negative because compressed, and y1, this is the amount of displacement m1 has. The effect on k3 will be, it will extend. So the expression for k3 or expression for del L3 is plus y1 plus for extension, and y1 is the amount of displacement. In case of k4, there will be no effect on k4, so we don't write it. Is M1 stays at its original position where M2 moves upward at a displacement y2. Let's see how it affects the springs. So considering the first spring, it will not have any effect for the movement of M2 since M1 is not moving. So we don't write anything in the expression, in the spring expression. There will be effect on K3. It will compress, so we write for K3 negative y2, and for K4 it will extend, so we write in its expression as plus y2. So now we have three springs displacement in terms of y1 and y2. In fourth step, we obtain equation of motion. So for free vibration we get this expression, and for forced vibration we get this expression where on the right hand side we have Ft, which is the external force. So substituting this three spring displacement in equation 1 and 2, we get this kind of form. We just substitute these three values in equation 1 and 2 and we get these values. Okay, so then our next step is to linearize the equation of motion. So since the equations are already linearized, we need to consider static equilibrium condition where y1 and y2 are 0, that has been mentioned in the problem, and also Ft equals to 0, which is also mentioned in the problem. And since the displacements are 0, so their acceleration will be also 0. So considering this static equilibrium, if we just look at equation 3 and 4, we'll get these terms as 0. So the equation 3 becomes K12 del L static negative m1g negative K3 del L3 static equals 0. And from equation 4 we get all this term as 0, so it becomes K3 del L3 static negative m2j g minus K4 del L4 static equals 0. So once we get this kind of expression, now what we want to do, we want to substitute these two values into equation 3 and 4, and the equation becomes a bit simple, which looks like this. So what we did, we actually substitute these two equations into equation 3 and 4 respectively, and we rearrange it to get this kind of expression where we have first acceleration, then we have y1 displacement, then we have y2 displacement, and then we have force component. So once we get this rearranged simpler equation form, we want to form matrix. How do we form this matrix? Let's consider y1 dot dot and y2 dot dot, and let's consider first equation. So from first equation, the coefficient of y1 is m1, so we write m1. There is no y2 dot dot in this equation, so we write 0 here. In considering this equation, we don't have any y1 dot dot, so that's why the coefficient becomes 0. We have y2 dot dot, so we write coefficient y2 as m2, and that's how we get mass matrix times y dot dot. Next is we want to form K matrix, which is stiffness matrix. And for stiffness matrix, we want to get y1 and y2 coefficient. So again, look at this first equation where y1 has a coefficient k12 plus k3, so we write k12 plus k3, and y2 coefficient has negative k3, so we write negative k3. Similar way in this second equation, for y1 the coefficient is negative k3, so we write negative k3. For coefficient y2 we have k3 plus k4, so we write k3 plus k4, and that's our stiffness matrix. Lastly, I found force vector, which is for first equation we don't have anything on the right hand side, so we write 0. For second equation we have force, external force, so we write FO, and then we keep cos omega t outside, and this is our force vector. So that is our second answer, which is the expression of motion in matrix form. Step is to solve the linearized equation of motion. So starting with the first one, which is the solution of undamped free vibration, where we take this matrix determined as null. So let's first form this matrix, which is K minus omega n square m. So here is our K matrix. This is our first element, K1, 2 plus K3. We take this value here, then we consider negative omega square, so we write negative omega square. Then we need to consider first element of mass matrix, which is M1, so we write M1, and that's how our first element of this matrix form, K1, 2 plus K3 negative omega n square M1. So for second element, again we consider similar way the second element of K matrix, which is negative K3. Then we need to consider negative omega n square, and then we need to consider second element of mass matrix, which is 0, so we just write negative K3. Same thing will happen for third element of K matrix, because it will be only K3, because third element of mass matrix is also 0, so we get negative K3. For fourth element, we get fourth element of K matrix, which is K3 plus K4, so we write K3 plus K4 negative omega square, and then we take fourth element of mass, which is M2, so we write M2. It's once we get this K minus omega n square m, it's better to substitute all the values we get, so it becomes a bit simpler. So that's what we did. These values are given in our problems. We just substitute this value into the matrix. Next step is to get the determinant of this matrix. And how do we get the determinant? So we take A, and this is D, so we take AD, which is these values, then negative, and then we take B and C, which is this term. So once we multiply it and rearrange it, we get this kind of form, which is the quadratic algebraic equation solution. So once we get this kind of form, we know the solution, which is x equal negative b plus minus root square b square minus 4ac by 2a. Exactly same thing we'll do for omega n square. So you can understand from this equation that we'll get 2 omega n square value, and that's what we get. Once we get 2 omega n square value, then we find 2 omega n square, then we get 2 omega n value, and that is our 2 natural frequency of the system. And then we found the natural frequency in terms of hertz. To know that, we need to use K minus omega n square m matrix times y1 and y2. Now this y1 and y2 are the amplitude of vibration motion. So you can understand that we'll have 2 equations, and we just use any one equation from this matrix. So we just select the first equations, and the equation become this term of this matrix times y1, and then this element of matrix times y2, and we get this expression. Once we get this equation, what we want to do, we want to get y2 by y1 ratio. So when we get y2 by y1 ratio, which is the amplitude of motion ratio, we just want to substitute omega n square values here into this equation, and just few minutes ago we just found that we get 2 omega n square value, so we substitute 2 omega n value and we get 2 ratios. So for first ratio we get negative 0.22, and the second ratio we get 2.22. Please feel free to pause it and calculate and match with this value. Alright, so once we get these 2 ratios, now we want to look for the mode. As you already know, mode is denoted as chi. So chi is a vector which can represent like 1, which will be always 1, first element will be always 1, and the ratio. So if you just look back, our first ratio was negative 0.22, so we just replace here 0.22. Because this is negative, it means they will vibrate in the opposite direction. So let's try to see how the system will vibrate at fast natural frequency, which in our case for fast natural frequency was, let's go back a bit earlier, our fast natural frequency was 9.04 Hz. So at 9.0 Hz, this is at 9.0 Hz, we get this mode shape where once the mass 1 moves upward at a displacement y, then the mass 2 moves downward at a displacement 0.22. Alright, for second mode, which is denoted as chi2, the element is, first element is 1, the second element is the ratio, second ratio, which we get 2.22. So because this is positive ratio, so their mass 1 and mass 2 displacement will be in the same direction. So here we get, once m1 move upward at a displacement y, so mass 2 will move in the same direction, which is upward, at a displacement 2.2 times of y. And that's our mode shape of the system. So that is our third answer. For particular solution, which is for force vibration, we already know how to find amplitude of particular solution. So we need to use Cramer's rule, and for Cramer's rule we get 2 amplitude, y1p and y2p, and they are expressed like this. The determinant of A1 matrix, now A1 matrix is like this. This first column is replaced by this first column of this matrix, which is this column. This column is replaced by force vector. So force vector is OFO, so we just write OFO in this matrix, and that's our A1 matrix. And for A2 matrix, we just replace second column. So in this vector, we just replace this second column with this force vector, which is OFO. So this determinant A1 means you substitute force vector in first column, and 2 means you substitute force vector in second column, and the denominator is just determinant of this matrix. So we get this. Now once we get all the determinant which we get in this in these slides, you can see omega, capital omega. Capital omega denotes force frequency. So once we get all the determinant of this fake matrix, we just replace this value into y1p and y2p, and the expression becomes like this. Now we want to plot y1p and y2p against force frequency. So horizontal distance is a force frequency and the vertical axis represents amplitude, particular solution amplitude. We need to consider three cases. First case is when the force frequency is 0. So once omega equals to 0, from these two expression we get the value of y1p and y2p, and just we want to plot this value qualitatively. Second case is when these denominator of the amplitude becomes 0. Once the denominator of amplitude becomes 0, force frequency becomes the frequency of natural frequency, which is 56.78 and 27.85. So we get two natural frequency which are equal to the force frequency, or in different way, force frequency are equal to the natural frequencies of the two degrees of freedom. So once we get these values, the amplitude of the particular solution become very high. So here is this two values where we get infinity amplitude. Now you can say from this two expression that y1p numerator is only a constant, so it cannot be 0. However, y2p's numerator has the expression which can be 0. Let's consider this is 0. So from considering this, we get omega equals to 54.77 radian per second, which is between two natural frequencies, and that point we called as null point. So at null point, for y2p the value amplitude is 0. That means at that point the vibration is absent, even the frequency is 54.7. And that's the fourth answer for our questions. Hope that will help you. Thanks for watching.